curves. So let's recall that for a function y, if f is continuous on the closed interval and that interval is partitioned into n subintervals of equal length, which we will determine as delta x equals b minus a over n, then we know that this limiting summation, so the areas of all the rectangles added up, where n goes from 1 to infinity, becomes the definite integration, from a to b of f of x dx. So this right here is the area under the curve, as I'm going to show you right here. So if f of x is a non-negative integral over a closed interval, then the area under the curve of this function from a to b is this right here. So what this is telling us is that we can find the area under the curve if I take the sum of a bunch of areas of little rectangles and we take the number of rectangles to infinity. And so that is what we're going to be doing here. So this means that we can think of this area as the sum of a bunch of rectangles, as you can see right here, from A to B. Take this number of rectangles to infinity, so these are super thin. And what we're going to do now, and we did this earlier, so what we're going to do now is we're going to take this to the next level. And in that level, what we're going to do is we're going to do this between two curves. Okay? So now, we're going to extend this concept to the area between two curves by changing our point of view. We're going to look at the previous definition as an area between the function f of x and y equals 0. So this is a function, and we're going to take the x-axis, which is y equals 0, as another function. Since each of the infinite rectangles have equal widths, it is just the height of the rectangle that matters the most, or the length of each rectangle. So this is the only thing that really matters the most. And we can find the length of each of these little rectangles that are occurring across the spectrum of this region by simply taking the value of the top of the rectangle minus the value from the bottom of the rectangle. Top minus the bottom. Okay? And when we do that, we can get this area. So the area between two curves, this is a rectangular approach, which is the approach I'm going to use the most, or exclusively really, is here's my region. I'm going to draw a little representative line in here, segment, that's going to represent my rectangle. This is to help me find the upper and lower part. What is it touching? What's the upper curve? What's the lower curve? And so that's what we're going to be doing here. It's the upper minus the lower. So in this case right here, oh, I forgot to label this one as g of x. So this is the upper curve is on g of x. The lower curve is f of x in this region. And so that's why we have g of x minus f of x. So this is how we're going to do it. Okay? In an area approach, let's use this here so you understand the concept of it. It's the same thing as we would do before. If I want to find the area of this region right here, I can find the area under the top curve all the way to the x-axis, and then the area on the bottom curve all the way to the x-axis, and then just subtract those two things. And so you end up with basically the same thing. That's what we were doing up here. This is a visual for the area. Okay? So this is the area between two curves. Let's go ahead and take a look and see what I have going on here. So I have some examples I want to do. So we're going to do this example, which I have written right over here. So how do I do these problems? What was our approach? What are we going to be trying? We're going to find R, which is a region in the first quadrant enclosed by two graphs. So your first process that you have to do is you have to draw this region if it's not given to you already. Okay? And so when it doesn't give you quadrants or A and B, then the A and B are determined by points of intersection of these two graphs. So this I'm going to go by ones. This one I know already. I'm going to go by threes. So if I take that one right there, 0, 0. If I plug in 1, I go to 3. If I plug in 2, there's a 6, and 3 goes to 9. And so I have this line going through those points right there in the first quadrant. So this is y equals 3x. If I graph the squared one, it also starts at 0, 0. 1 goes to 1. 2 goes to 4. And 3 goes to 9. And so I have this curve right here. So where is the region between these two curves? That's this region right here. Okay, so draw your curve. The next thing you have to do, okay, is you have to identify each of the points of intersection. This point down here is 0, 0, and this point right here is 3, 9. You have to find those. You can find them by algebraic approaches. If you are allowed a calculator, you can find them on the calculator. We're going to show you examples of all those. This was basically the algebraic approach to it. Okay, once we have that, we have our boundaries, we have our points of intersection labeled, and then the next thing you draw is that representative segment. Okay, this is going to represent, you want this visual in your mind. Okay, I know you can probably do it without it, but you put it in anyway. You'll understand later as we do the rest of this unit. This helps me find the upper and the lower. Okay, and once I have that set up and I've identified the upper and the lower, then I am ready to begin. So to find the area between these curves, it's going to be the integration, and we're going to be going across the x-axis like so. Okay, I'm going to do a dx. I'm going to start at 0. I'm going to end at 3. So from 0 to 3. And then we got to find the upper curve. The upper curve is this line. This line is 3x. Always put these functions in parentheses. You'll understand again later. And the lower curve is right here, which is y equals x squared. And so we have x squared. And don't forget your dx on the end. So that is the integration setup. Okay, once you have that, at this point it's either solve it by hand or you do it on a calculator. In this case, we're going to solve it by hand. So we're going to integrate all this out. This becomes the integration from 0 to 3 of 3x dx minus integration from 0 to 3 of x squared dx. And so we keep on going, and this right here becomes 3x squared over 2, and this will be x to the third over 3, and these are evaluated from 0 to 3. Okay, the next step is very important, and you must show this if you're doing this by hand. It is required, both from me and also for the AP. If you're solving this by hand, you need to plug in your numbers and show it where you've plugged them in. Don't try and simplify at the same time. Just literally write it in without simplifying. That's the upper minus the lower. Oh, but I know it's 0 already. It doesn't matter. Then you need to show that line. Once you have that line, then you can just give me the answer. You can work this out however you want and get the final answer, and that answer is 9 over 2, and you should be done there. Okay? So, those are some things you want to make sure that you write down in the process that you follow. Here is another example right here we're going to do. Find the area of the region bounded by the graphs y equals x squared plus 3, y equals x equals 0, and x equals 2. So, again, the first thing you have to do is you have to draw this region. Notice the x's go from 0 to 2, so that's really the only parts I need to graph. Okay, don't get carried away. I'm only going out here to 2. Okay, so I have a y-axis, x equals 0. I have a line here, x equals 2. And then I need to draw these graphs. So I know that I have to go pretty high at 2. This is going to be, take the biggest one and plug in 2. You'll see that you're going to get what? 2 squared, that's going to be 4, plus 3 is 7. So I'm going to have to go up to at least 7. I can go by 1s. I'm just going to go by 2s. because I'm just looking for the shape. I don't really care so much about accuracy too much. This was going to start at 0, 3, and so I have this curvature. 1 is going to go to 4. So I have this quadratic curvature, it does that. And then I have a line here, so be careful because of your scale. 2 is going to go to 4. I don't know why I said that. 2 is going to go to 2, excuse me. And then 1 is going to go to 1, so that's right about here. And so this is the line down below. So be careful on when you do this thing. And then this is my region between all 4 of those pieces. So this right here is y equals x squared, x equals 2, y equals x. And so that's the region I want right here. And so I need to find all of these points of intersection. Okay, so I need to know this one, which is 0, 0. This one is 0, 3. This one is 2, 2. And this one is 2, 7. We know those because that's how we got it when we graphed it. Okay, so once I have all 4 corners, all the points of intersection labeled, then I'm going to draw my representative segment to identify the upper and the lower, and so then I can write my area. So the area is going to be from 0 to 2. The upper curve, x squared plus 3, minus the lower curve, which is just x, and this is what I'm going to take the integration of. And you can just do each piece that's in here. X to the third over 3, 3x, x squared over 2, evaluate from 0 to 2. Upper, and then minus the lower. And then you can work that out and get your final answer here, which is 20 over 3. Okay? So I'm going to show you the notes that I wrote so you can get all the little side pieces that I've written out for you. So go ahead and take a pause right here. And here's the last one, which I already did. You saw that one. Okay, so let's go ahead and take a look at the next example that I have. So now I have this. So I gave you a picture. You'll notice that there are now 2 regions. I've gave you the graph already, but you'll notice that I don't have all the points of intersection, and I'd have to find those. So the graph is done. Okay, we're going to find the area of each piece, but before I can do that, I got to find these points of intersection. Now these are pretty obvious. This is going to be 0, 2. This is going to be 0, 0. These may not be so obvious. This one right here is when that is equal to 0. So when is 2 minus x to the third equal to 0? And we can solve this out. And you end up getting x is equal to the cube root of 2. So that's the name of that point right there, the cube root of 2 comma 0. But what about that one? Well, that one up there is when is the tangent of x equal to 2 minus x to the third. So you can see that that's a little bit more involved. You cannot do this by hand. You'd have to do this on the calculator. And so we can go into a graphing form. We can graph, make sure we're in radian mode. Yep. So we're going to graph the tangent. And we're going to graph 2 minus x to the third. And so we need to see that point of intersection right there. Okay, so we go to Menu, 6, Analyze the Graph, Intersection Point, and we just find that point using our calculator. And you write that number down. You write both of them down, the X and the Y. I know it's kind of hard to see there, but I'll write it out for you. Why do I need to have both of them? Just because. So when is this here equal to what value of X? When X is equal to 0.902155. Do not round this off. You write down all the decimal points given to you. This is very important. If you round it off, you will be wrong. It will not give you the right answer in your work. So this is what X is approximately equal to, right there. So at this point, you have two choices. You can keep this number and continue this problem and write this number every single time. Or, at this point, you can assign a letter to this, other than X. Usually what we do is we assign like a capital letter A or something like that, A or B or whatever, if you have more than one. And you simply say this number right here is going to be stored in A. So this number is A. And you can actually take this number, okay, we have to go into another one over here, but you see the store feature on your calculator right here? The store button? So if I go into a new page, I can type this number in, 0.902155, and I can store it in, oh, you can't see what I'm doing. So take that decimal point and I hit that button store, it gets that little arrow, and you store it in capital A, and you can just leave it like that. And then you hit enter, and then every time I type the letter, this A, it will type in that number. So that number has been stored in A now, and I can actually use it in my calculations without having to type that whole number in. That is an option available to you. Okay? So once we have this, we're going to find region R and S. Find the area of each region, so let's find the area of R. So I need to have my little representative rectangle in here. And what you'll notice here, and what you need to look for, is does this rectangle have the top and the bottom stay the same across the entire region? And what happens here is, at this point, it doesn't. It switches. On this side of this line, the top curve is different than the top curve over here. When that occurs, you're going to have to write your integration as a split. And it splits at this point right here. So, in that case, our area of R is going to be the integration from 0 to that point, which is that number. And you can write it as 0 to, and I'll do it with the number this time, 0.2155. Okay, it's the upper curve, which is the tangent of X, minus the lower curve, which is 0. And then to this, we're going to add the integration from this point onward with this rectangle, where the upper curve is 2 minus x to the third, and the lower curve is 0. And then we're going to start at this point, and so I can write that in decimal down here again, or I can simply put A, and end at this number, which is the square root, the cube root of 2. Okay? So usually in this situation right here, because we had to find the point with a calculator, this is a calculator problem. So let's go type this into our calculator so you can see how it's done. So we're going to go into menu, we're going to go to calculus, we're going to do an integral, and our limits are from 0 to that number, and I can type in 0.902155. I'm going to do the tangent of x dx plus and I'm going to do menu, interval, calculus first, then interval, and I'm going to go from this number, which I can type again, or I can simply just type in the letter A. And up here, the cube root of 2. And this in here is going to make sure you put it in parentheses, 2 minus x to the third dx. So, see, I can use the number or I can use the letter. And then you hit Control and Enter, and you get this number right here. So my area is approximately 0.729. And then the final answer, you can round off to 3 decimal places. Okay? All right. So what about region S? So this one's pretty straightforward, so we're going to be doing it again. So we're going to draw a little representative rectangle in here, or a little segment, indicating that the top curve is going to be the 2 minus x to the third, and the bottom curve is the tangent of x. And so this area is going to be an integration from 0 to that number, from 0 to a, okay, of what? The top curve minus the bottom curve, like so. Make sure you write it out, and then you can use a calculator and you can approximate this out. So for the sake of time, I'll just tell you that this is what you should get, and you should check that to make sure that you do. Okay? So let's look at some more stuff. Namely, what happens if I can't do an up and down segment? In these situations, if you look right here, the way the graphs are drawn, I can't draw a vertical representative segment. It doesn't have an upper or lower curve. Over here it has an upper, but it doesn't have a lower. And over here, you'll notice that if I drew a vertical one, this rectangle right here will touch the same curve at the top and the bottom, and I can't have that either. So in this situation, we're going to draw and find the area between curves using a dy. Okay? And so the process is exactly the same, and you should take a pause here and write all this out. But in this case, instead of going top minus bottom, we're going to do right minus left. We'll draw the rectangle this way, and it goes to the y-axis, so you can see why it's a dy. So the things to keep in mind here is this. If I'm going to use a horizontal segment, I have to make sure my equations are solved for x in terms of y. So I need x equals. If they are not, you'll be incorrect, okay? And then we're going to do the limits are based off of the points of intersection, but the y coordinates of those points. Okay? So let's go ahead and take a look at this and see if we have some examples that we can look at. So I have this example right here at the bottom. So find the area of the region bounded by the curves y equals x minus 1 and x equals this right here, 1/2 y squared minus 3. So we need to graph this out. Your first task is to graph this region so that you can see it. One solve for y, the other one solve for x, so keep that in mind. But you can draw this however you want. I'm going to show you to do it real quickly here. You can do it on the calculator if you have the ability to do so. So the numbers that I need here real quickly is, this is going to be a 5, and for the sake of the time on the video, the quadratic that's sitting over here is going to go through that point right there, this one right here, this one down here, and it's going to go that point right there. So this is my parabola on its side. Okay, and then I have to draw the line segment, which is just this line right here. So it's going to have a y-intercept here, and then a slope of 1, up 1 over 1. And it's going to go all the way up to that one. This point should be right about here. Sorry, I just got it in the wrong spot. But you'll get the idea. This point right here, because I'm not on the graph properly. But again, this point of intersection is what's important. That point of intersection is what is important. Okay? And what are those values? So we need to find those. And we can find them using whatever means we have available to us. Most likely what you do is you set it up as an algebraic approach. So when is, now we can take this right here, we need to solve this for x. So x equals, move things around, and we get x equals y plus 1. So when are these two things equal? Okay, and we can work that out and get that solution. But we also graphed it so we know also. So this one right here is a -1, -2, and this one over here is 5 and 4. Okay, this is my region we're going to be using, finding. Once I have the endpoints right there, so again, algebraically is when is this thing right here equal to this right there, and you can solve that out, and you would have got these two y values. Now, I can't go up and down because of that right there. I can't have the same top and bottom land on the same curve. That we cannot have. So this is a candidate to go side to side. So we draw a representative rectangle in here, or segment, and we get this curve is right and this curve is left. Okay, we have the points of intersection. We know it's going to be a dy. We solved this, all equations for x equals. We're good to go. So my area is going to be the integration, and we'll do the limits in just a minute. It's going to be the right minus the left dy. Okay, and then what is the y values ranging from? The y values are ranging from -2 up to 4. So remember, in a dy you have to do the y coordinates. This is why you list the whole point, not just the one you want, because you never know what's going to happen or what you'll need. Okay, so once I have that, then I can clean all this up and I can integrate it. Simplify where you can so that you're not doing extra work for yourself. -2 to 4. And as we clean this up, you're going to get a y minus a 1/2 y squared plus a 4 dy. And then we can integrate each of these pieces. Okay, so y squared over 2. This is y3 over 3, so this will be 1/6. And then this over here will be 4y. Evaluate from -2 to 4. And then we plug these numbers in. So it's going to be 4 squared over 2, 4 cubed over 6. And then this is going to be 4 times 4. Minus the lower. -2 squared over 2. -2 cubed over 6. And 4 times -2. And then you can work all this out and get your answer here, and when you do, you should get 18. Okay? So let's take a look at that. I'm going to move this over here. I'm going to allow you to see the notes for that. Take a quick pause here to zoom in and copy those notes out. Okay, so here we go. Let's look at the next example that I have for you. Here's a region, first quadrant, bounded by the x-axis. The graph's y equals natural log, y equals 4 minus x. Find the region R, and so we need to graph these things out. You'll see the normal theme is the same all the time. Okay, the natural log graph I know goes through 0, 1. Okay, and as I go through this stuff and I draw this curve, and again, everything's not going to be to scale or anything like that. If I draw the line 4 minus x, it's going to come up from here. We can just plug in some numbers in here. If I plug in a 1, it's going to be at 3. If I plug in 2, it's going to be at 2. So 2 is at 2. 4 is at 0. And so I have this line right here. So here's my region R. This is y equals the natural log of x. This is y equals 4 minus x. This point I need to find, and this is region R. Okay? And so what you'll notice here in this problem is we got to find that point, and that point is found by finding when is the natural log of x equal to 4 minus x. So this is clearly going to be a calculator problem, and so we would type this in on our calculator, graph it out. So we have, the first one is the natural log of x, and then we're going to have the line 4 minus x. Okay, and we need to go to menu, and we need to find that point of intersection. So we want to start there, and then we want to slide across and find that point. I'm going to pull it up so I can see it. And again, you need the entire point, 2.92627 and 1.07373. So I need that entire point. Okay? Since there's two of them there, and I don't know what's going on here, am I going to do a dy this way, or am I going to do a dx this way? I don't know, but both options are available, so I can just simply do what we talked about. We can store these values. Okay, I can say 2.92627 can get stored as A, and 1.07373 can get stored as B. And I can store those on my calculator. I'd have to go into here and do it like I did before. And just type the number, 2.92627. I'm going to store that. I'm going to control and store that as A. And then I'm going to type in 1.07373, and I'm going to store that as B. So you can see that if I type in A, I'm going to get A, and if I type B, I'm going to get B. Okay? And this allows me not to have to write those numbers out when I do this. So what happens if I do a dx? If I do a dx, like everything's set up for a dx, y equals and all that kind of stuff. So if I do that, what's going to happen is I see that I split right here at that point, which is fine. I just have to do it in that fashion. So as a dx, my area is going to be the integration from 1 to that x value, from 1 to a, and it's going to be the upper minus the lower, which is 0. So the upper is the natural log of x, and then this one's going to go from a to 4, and it's going to be from this point down, so it's going to be 4 minus x dx. Okay? So I can do this on the calculator and work this out and get an answer. Okay? What if I want to go side to side? What if I want to do it this way? Could I? Yes, I can, but remember, you have to set it up for that, which means these equations have to be solved for x. So I'd have to take y equals the natural log of x and rewrite it as x equals e to the y, and I have to take y equals 4 minus x and rewrite it as x equals 4 minus y. When I have done that, then I can do the dy approach. Okay? And so then my area here is going to be the integration from 0 to this y value, from 0 to b, the right curve, which is the line, minus the left one, which is the log, dy. And if I type that in the calculator, if I type either one in the calculator, I'm going to get 1.792, and that's how you can do that one. Okay, so we have one more left. since we've done this enough, I'm just gonna show you the example. I'm not gonna work through it for the sake of time on the video. I'm gonna show you the final version of it. And so what happens if I have a curve that intersects more than once? Okay, so if you look over here on this curve over here, you'll notice that I have a parabola right here, y equals x squared plus 4x, and this over here is a cubic, g of x equals 12x plus x squared minus 2x to the third. So the quadratic is right here, and the cubic, you can see, crosses that quadratic, and there is two separate regions here. And what happened is the upper minus lower switches in both regions. So I have to learn to split this out, which means I got to find the points of intersection, which we did algebraically. This would be an algebraic problem. I got an intersection at -2, at 0, and at +2, so we'd have to find those values. We draw our sketch, and then in the first region right here, from -2 to 0, the upper curve is the quadratic, the lower curve is the cubic, so it's the upper minus the lower. And in this region, from 0 to 2, it switches. So the upper is the cubic, the lower is the quadratic. So this is why it's important to write it in parentheses. And so then what you want to do next is you want to make sure you simplify this first. Don't go and try and integrate this, it's just too much. Okay? It gets really complicated afterwards, you get really long answers. If I combine like terms in here, I get it simplified to that. Combine like terms in here, I get it simplified to that. And then I integrate these pieces. Usually, like I said, this will be by hand. And then upper minus lower, upper minus lower. Then I can work all this out, and I end up with the answer 16. So this is how we find the area between two curves. All the different approaches, either dy's or dx's. And let me know if you have any questions, and we'll talk about it next time.